recording, start broadcast. Okay, so what I will do is that go to our class here, announcements, plus, okay, join us at 954-9053-8047 on Zoom. Okay, then paste. Okay. Okay, I sent it. Just in case people cannot see it. All right, so at this moment, what I would like to do is to continue with our examples in, and let me just 1 second here, increase the volume, yeah. I would like to, tell me whether this back distracts you. I had it from a Zoom yesterday, so I don't want to take time and change it. Is this okay? The picture that I have behind me? Do you want
it's okay. Professor, I'm getting an echo on your end, like everything you say is echoing.
I'll tell you why. I have unmuted this one here. And, okay. You get it because
I think it went away because I don't hear it now.
Oh, yeah. Can you hear it now?
No, I think you're good now. Sorry about that.
No problem. No problem. Okay, so let me now do this. Go to
Dr. Katay.
Yes.
I was wondering in one of your examples if you could discuss how the voltage changes from one end of the transmission line to the other.
Sure, absolutely. Yes, I can do that. So this is not the one I'm looking for, but I will start a new one. Okay. So let's assume I will start with this discussion because I think many of you will have the same question. And also I wanted to tell you, probably you hear the same thing. I wanted to tell you that we are good. I think that the echo is here and it's because of my iPad. So you can try to, I don't know how else I've reduced the voice and I've reduced, I mute it also, but I don't know why for some reason it keeps having it. So what I suggest that I do, and that is an important question because others will probably ask me, is to practically do the following, do an example. So say here, I will write the example and say, consider a transmission line with a load ZL equals, say, normalized to 2, and find the voltage and current so total voltage plus current on the line. Assume that the line has a length of D equals 0.75 lambda. Okay? All right, what I'm doing is solution. What I'm giving, in fact, is this one and this one. I'm giving these two very important numbers, as you know. Okay. And what I'm trying to do is to find out exactly what they're asking me. So I'm going to draw the line. As I said, you will do that, even if it has been provided as a figure. Okay, so what I have here is a load at the end. No, not this one. Okay, this one. I have a load at the end. ZL equals 2. And I have a length D equals 0.75. Okay, we are going to solve it in two different ways. First of all, with the equations and then with the Smith chart. So what do we know? I'm going to write the equations that what I have suggested for you is to put them on a separate piece of paper and have it available for you. So what I'm going to do here is this number one. So A solution. We know that V of Z total has two parts, V plus of Z plus V minus of Z. And this is equal to V naught plus E to the minus J beta Z plus V naught minus E to the J beta Z. And also what we have created, we have assumed here is that this is the Z-axis. I also want to remind you, this is here, Z equals 0. This is Z equals D. And if I am anywhere here on this part of the line, and then also what I have done here is to put A prime, B prime. And then if I am at that point, C prime, then I know that this one, in fact, I can erase this part here to make space and put 0.75 down there. And then what I can do here is to assume that this is, if I am at CC prime, this is going to be Z. And this is Z prime. Okay, so now we know that. Also, for the voltage, we know that V naught minus. Rather before I go there. Okay, so then we know that. What is the other thing that we know? That at the end of the line, the reflection coefficient. So what else we know? At Z equals D, we have gamma L to be equal to ZL. See, if I give you normalized, you don't even need to know how much your Z naught is. All right, if I want to do these types of calculations. You will find out that you will need it, of course, at some point later, but for this now and for the Smith chart, you will not need Z naught because everything is normalized. So this is, I write it in this form. And that's 2 minus 1 over, say, 3. is 1/3. Say 0.33 approximately. Also, yes.
Oh, sorry to interrupt. In your initial equation, the VZ equals V plus Z plus V minus Z. Shouldn't that be a difference since we're trying to find the VZ total, which is the potential difference between the two?
What do you mean?
No, the equation is correct.
Yeah, I know, but the question is,
Because we're trying to find the voltage difference, correct?
that's
Between
the
the two lines.
Oh, between the A and A prime, that's what you mean, is that?
Yeah.
Okay, that's the voltage difference. VZ applies here, applies like this. And I of Z flows like that here, and like this here. And they are the total.
So you're just assuming that the V minus Z will have a negative value so that
Not
they
necessarily,
subtract?
well, depending on the load, because that's what I was gonna write. Gamma L is nothing else but V minus at D divided by V plus at D. And according to that is gonna be V0 minus over V0 plus at E at E J2 beta D. So when you calculate 0.33, then practically you find from that your V0 minus over V0 plus equals 0.33 e to the minus J2 beta D. Okay, so practically you find a ratio between these two, and what the V minus is gonna be, they're gonna be complex numbers, obviously. What the V minus is gonna be compared to V plus depends on the load. It could be anything, like any complex number. It will have amplitude and phase, obviously, and it could have any amplitude, as you will see, from 0 to a number, and any phase. Okay. So having said that, how much is 2 beta D? 2 beta D is 4 pi over lambda times 0.75 lambda. And 75 is 3/4 of lambda. So it's going to be 4 pi over lambda times 3 lambda over 4, which is 3 pi. Okay. And 3 pi, what is it? So E to the minus J 3 pi, how much is that? Do you see that? Because E to the minus J 3 pi, because is equal to cosine 3 pi minus J sine 3 pi, which is -1. So practically what we have is V naught minus over V naught plus equals minus 0.33. It's not going to be, if D was something else, it could have been any complex number. I just selected D to simplify our calculations. Okay? So now I can go to V of Z.
Professor?
Yes,
Excuse me.
sure.
On the equation V naught minus over V naught plus equals to 0.33 of exponential of negative J2 pi d,
Yeah.
J2 beta d. Where did that negative on the phase come from?
So from here, if you take this relationship that gamma L is the reflection coefficient of the reflected wave over this, the reflection coefficient is, by definition is the reflected over the incident voltage wave, then the reflected voltage wave is this one. The incident voltage wave is this one. And when you take the ratio of the two at the end of the line is this one.
Yeah. I get that part. What I was asking is like on the one you highlighted is the positive J2 beta D, and on the next
Yeah,
equation it
because
becomes like,
see, then from this one, I'm solving for V minus 0 minus over V0 plus. So I divide by e to the J2 beta D. I move e to the J beta D to the other side of the equation. So practically here, I will write it and then, so I have to divide.
oh, I see. Sorry.
Yeah, no, that's okay. Yeah. So V naught minus over V naught plus then becomes that, which then I can go and replace. And then I have V naught plus as a constant. I still have not found this, and I will not be able to find it unless I have information about the source, because that is what the source produces, all right? So, but here I can put minus, excuse me, no, that is, sorry about that, E to the minus J beta Z, and then I have minus 0.33 E to the J beta Z, all right, from here, all right? And then, so I have that. Now, what is interesting, which I would like to do next, is to find the magnitude of V of Z and to find the phase magnitude of V of Z. So the magnitude is going to be, if we were to write that, it will be the magnitude of V naught plus, and then it's going to be the magnitude of this complex number. And if you were to write it, for example, you would find, I'm not sure I can draw it for you, but I'm not sure I can really give you a very concise expression, but I will try. So it's going to be then V naught plus, and then it's cosine of beta Z minus J sine of beta Z, and then times, oh no, excuse me, I have more. And then is minus 0.33 cosine of beta Z minus J 0.33 sine of beta Z. And that is going to give me V naught plus, and it's going to be 0.66 cosine beta Z minus J 1.33 sine beta Z. Now this is then you can proceed from there, for example, and then you will find an expression, all right, which is not going to be easy to find in a simple functional form. What people are doing, however, from here is to find the maxima and the minima of V. And what they have found is Well, I can proceed. Let me do it for the sake of the problem. So here, the magnitude that I have inside this, all right, the magnitude of this exponent, complex number is going to be, how much is 0.6? 0.66, let me do it like that, square, cosine square of beta z plus 0.33 square sine square of beta z. All right. And I can rewrite that. And then let me see exactly how much this is going to be. I can rewrite this.
Dr. Katehi,
Yeah.
in the second to last line, should it be 1.33 squared?
Ah, yeah. Thank you. Why did I put 0? Because I don't know. My brain is sleeping. Okay, 1. So let me find out how much this is. Square. So that is square root of 0.435, say 0.36, cosine square beta z plus, and then 1.33 square root, no, 1.33 square root is 1.76 or 77 approximately, sine square beta z, which in fact, this is going to make it v naught plus square root of 0.436. I take that part of out of sine square and I make this equal to 1 plus, and then if I take 1.77 minus 0.436, that becomes plus 1.3 sine square of beta z. That's a simpler one, definitely. All right, so now you do that, you can see this, but you don't have a very good sense of how that looks like, all right? It's like a constant line plus a second power of sine. So if you look at this, if you look at the, and then in fact the square root, if you like, just to make it more, I will put it like 1/2 here. All right, so you can see this. So this is the magnitude of V of Z. If I were to go to MATLAB, which in fact, I will ask you to do that. And I will open a small, if you do this on MATLAB, and now that I have created the formula, I will give you that as a top hat question, but it's not gonna be on top hat, obviously. I will do it in a different way. I will open a small top hat exercise on our canvas, and I will just ask you to upload some of what you found. Go to MATLAB or any other thing. If you have a small program, you can do whatever, however you want to do it. You want to do it also by hand, do it that and find for me how, which I will show you, but I'm not going to be accurate, how your V of Z is going to look. This one has a very important form, and it's called, now that brings me what I was planning to do today, that is called a very important word, and that is called the voltage standing wave. Why is it called the voltage standing wave? For the following. Let's try now approximately to plot it. Approximately. What I was going to do is, put this as z. And in fact, if I want to be correct here, since I have the means to do that, let me do it better. Okay, I'm not going to try this one. All right, so this is z. For z equals 0, which is the beginning of the line, this is the end of the line, all right? So the line is, if I want to be correct, I'll show you where the line is with a thicker line here. That's the line, the length of the line. And what I find from this, is that at z equals 0, this is 0.436 square root. And as a matter of fact, what is interesting is many times you may see it as a magnitude square, the standing wave. But here I'm going to do it as not with a square, but just as a simple magnitude. So 0.436 square root is exactly what we found before, 0.66. So it should be 0.66. So at z equals 0, the standing wave, which I'm going to show with red, if this is 1, say, if this is value 1, and if this is 2, so it starts at 0.66. Okay, then when beta z, so how much is the total beta z? We said beta d. So if this is here, when also I show that, you know how I'm gonna do it? I'm gonna put here beta z, where beta z at z equals 0 is 0, obviously. At z, this is at z equals 0, beta z is 0. And at z equals d, beta d is how much we found it. We found it here. It's 3 pi. Okay, so beta d is 3 pi. Okay, so also I remember those. So now I'm going to plot it as a function of this. At beta is equals 0, sine is 0, so it starts at 0.436. At beta z equals pi over 2, so now I can split it. This is going to be pi over 2, 3 pi. So let me see, pi over, no, it's going to be pi, I mean. So it's going to be pi over 2 here. So I need to have 3 pi's in there. So I will have pi over 2 here. I will have pi here. I will have pi, I will have 3 pi over 2 here. I will have 2 pi here. I will have 5 pi over 2 here. And I will have 3 pi here. Okay? And in fact, since this 3 pi is there, so let me, that does not help. I need to expand so I will go the 3 pi, it's not exactly that. Let me put here, we'll see. Pi over 2 here, pi here, and then it's 3 pi over 2, and it's 2 pi, and then it's 5 pi over 2, and then I will extend this one a little bit. All right, and so I will extend this one. Okay, I'm not that far. So this one here, it's pi. All right, that's better. Okay. All right, pi over 2. pi over 2 is 0.436 plus 1 because sine pi over 2 is 1. So at pi over 2 is going to get the value, it's going to go above 2, and it's going to be 0.436 plus 1.33. That's one, oh no, it's going to be 1.766, not above 2. So it's going to be here, here. And then at pi, sine goes to 0, it's going to go down here again. And then at 3 pi over 2, it's going to go here. And then 3 pi over 2 is going to go here. Okay. And then here. And then here. And then here. So now if I were to plot it, you should get a plot like that looks not sine, it's going to look like this. Okay. And that is called the voltage standing wave. And I'm not sure how how different, I mean, the more or less it's going to look like that, but whether it's sharper as it goes down to the deeps and it's flatter up there on the peaks, I don't know. It's going to depend, but I will give you an opportunity to do it on MATLAB, take a picture, put it there, and I will give you credits for that, just to go through this problem. And so this is very important. It's called the voltage standing wave. It is like the total voltage looks like this. The question is, how will the current look like? Okay, that is an important thing. So let's now look at the current. So this is part A. And now I'm going to part B. So the current, if you remember, is going to look like I plus of Z plus I minus of Z, which is going to be equal to I naught plus e to the minus j beta z plus I naught minus e to the j beta z, which according to our formula is going to be 1 over z naught. So let's write it here. V naught plus e to the minus j beta z. Let me remove it a little further down so it does not get cramped. Plus minus here, v naught minus over z naught. You need to remember the minus sign in front of this, e to the j beta z, where I will put here in parentheses. We know that v naught plus divided by I naught plus is z naught by definition. And v naught minus divided by I naught minus is minus z naught. You need to remember this minus sign. All right? And then it's here. So now from there, we had above plus, all right, in there. Now we are going to have a, we had a minus up there. We had here, if you look at this, so practically I will take this one and I will only change the sign. So the I of z, look at this. So I of z here, copy. From this, I will paste it. So practically, I will change only accordingly. What I'm going to find is, this is going to be I, this is going to be V naught, and this is going to be plus. So this is I of Z is V naught plus this. That's the only difference with V of Z. And therefore, what I find is that I of Z has the same form, which is kind of interesting here, and I will explain why. So I of z here is going to have the same, let me see, it's a minus, we found the square root. Okay, so here is what, and I will explain why that happens like this. This one is going to be the same with what we have for the voltage primarily. Not exactly, it's going to be different, sorry. Let me though find it. This one is going to be this one, because that can be a complex number. And then in here, if you remember, I will have 1.33 cosine of beta z. And then I will have minus j, and this is minus j sine in the first one, and plus is going to be minus 0.66 sine of beta z. That, and the difference with, look at the difference between the two. In the first one, in the voltage here, I have a minus J133 sine in the sine, and then in the current, I have 1.33 in the cosine. All right, so there is a difference, but when I try to get the square root of this, this is gonna give me V naught plus, and then I'm gonna have the square root of 1.33 square cosine square beta z plus, and then in fact, let me put it in a, because I cannot extend the square root. It's going to be 0.66 square sine square beta z. All right. And that is going to give us that I of z is going to be V naught plus, and then we are going to have 1.33. What did we find here? Okay, it's not exactly the values I got. I say I'm trying to do things fast. So that is correct. So 1.33 square, which is 1.33 square, 1.77. So this is going to give me 1.77 cosine square beta z plus 0.66 square 0.4, how much did I put there? 0.436 sine square. Which in fact gives us I of z magnitude of that, and then we have 177.346 is gonna make it 2.2, and Here I made a mistake. Why did I put V 1.733 instead of 1.7? Okay, that does not matter, but I have to correct it. So this one would have to be 0.77. All right. Okay, which is fine. I mean, it's not going to change the way it looks. It's going to go above 2, obviously, here. So I will erase these parts to be accurate. All right. So here is going to be 1.77 plus 0.436, 1.77 plus 1.77 plus 1.77 plus 0.436 is 2.2 plus 0.436 sine squared beta z. And that's 1/2. So that is the magnitude of the current. And that is called the current standing wave. The current standing wave. Okay. If we were to compare the two, so in fact here to be accurate, I will have to do this to make it point 2. I don't even know why I put that. 0.2. Okay. So what we have it here, and it's 0.2, and then, yeah. All right. So look at, they are very similar yet different. One has 0.22, and the other has 0.22, but the sine has a different coefficient in front of it. All right. So what I would like you to do is to make sure that I go through my calculations, and in fact, they are correct. And then I just want to make sure that this is 0.436, 177.22. Yeah. All right. Just make sure that my calculations are correct and then plot them. Now, why these standing waves are important? Because they give you an idea of the current standing wave is going to have a similar form with the voltage, but it's going to be different, obviously, in the magnitudes, all right? And different at where is the z equals 0 value. It's going to start at a much higher. The voltage standing wave is like that. The current standing wave, I would like you to do both. Just put them on MATLAB. You have the calculations. It's going to be something like this, but at a higher level because of the equation. Why are they important? Because they show you at what points on your line your voltage standing wave or your current standing wave have a minimum and where they have a peak. And this is important when you place online on a transmission line what we call your matching networks, which we're going to do all of next week. So it's important to know. But from the voltage and the current standing wave, there is another parameter that is defined, and that is called the voltage or the current standing wave ratio. So the ratio between the maximum and the minimum of the voltage current wave and the maximum and the minimum of a current standing wave are important. Why is that? Because they tell you how much the reflection is. In other words, if my load were 50 ohms, if the line here, ZL, were to be 50 ohms, my reflection coefficient would have been 0. And if my reflection coefficient would have been 0, so my voltage standing wave, it would have been all a straight line. So practically for a 0 reflection, so this is, let me put here red. So this one is for, let me see, 1 second. Let me do this. So for this one is for Z L to be, what did I say it was? Forgot already, 2 normalized. But if ZL normalized were to be 1, meaning Z naught, then the voltage standing wave ratio would have been something like that. All right, a straight line. And it would be equivalent to the value of V naught plus practically. So that would, which I don't know now because we don't know anything about the source, but it would have been this, and that, to put it, to make it green rather, and then say here that this would have been the voltage standing wave ratio for Z sub L normalized to be 1. So the further I deviate from this straight line, the green straight line, and I go around it, like in hops, all right, like hopping around it, the more the indication that I have a reflection coefficient. The higher the reflection coefficient at the end, the bigger the difference between the maxima and the minima of the standing wave. So considering that, what then we define is another important parameter, which is called, I will put it here, voltage, because next time we're going to do the whole thing on a Smith chart, voltage standing wave. All right. And the voltage standing wave, we write it as VSWR. And VSWR is V max over V min. Or rather, I would say, it's not right to put it this way. I will put V voltage max, V voltage min, even if some people may put the max and min inside. But now you say, do you have to really do all of these calculations to find it? No, what people have found out is that this is equivalent to 1 plus magnitude of gamma L, 1 minus magnitude of gamma L. The last thing, do you remember what is the largest value of the reflection coefficient and the smallest value of the reflection coefficient? How those could be? What those values are? Do you know? What is your reflection coefficient in best case scenario where your line is matched?
1.
The line matched?
Or are you asking about the reflection coefficient or the
Yes.
standing wave ratio? Oh, it should be 0.
It's 0, perfect. So the minimum value of gamma L, the minimum value you can have for gamma L is 0, right? What is the maximum value you can have for gamma L?
1.
Exactly. So let me now write it here. So this is minimum possible and maximum possible is 1. So What is the optimal value of the VSWR for matching? What is the VSWR when gamma L minimum is when gamma L is 0?
It's just V naught.
No, look at this. Look at my relationship. It's 1. When gamma L goes to 0, VSWR is 1. That's a ratio, right? That's why V naught does not show. It's not the VSWR standing wave. It's just the ratio of 2. That's why the V naught plus gets out of the picture. All right, because of the ratio.
Oh, I see. Yeah.
So it's 1. The optimum, the best, the lowest and optimal value for VSWR is 1. And the worst, when is this worse? Infinite. It can go so bad that it can become, why does it not show? Okay, I think this one is, all right, so it does not show on my screen, but I'll tell you VSWR for gamma L equals 1, and I think it just bumped me off on my other, is infinite, all right? Can you hear me?
Yes.
Yeah. Yes.
Perfect. So it does not show somehow, but it's infinite, which means that your VSWR1 is the optimal for matching. When I say match, it means match my line to a load, and we can put things in between the load and the line to match it. So we make the reflection coefficient 0, which says that we make the VSWR 1, and therefore the optimal case for VSWR is 1. Now, when we make components, and if you are to go and buy, say, a filter that somebody has designed, and you want to put it, or a low noise amplifier, at the input port, you want to know how much of a reflection this is going to create to your line if you enter a filter in there. And usually they give you as one of the parameters a VSWR. And good values for VSWR is 1.1. You can never get 0 at a frequency band. You can get 0 at one frequency only. But as people operate over a frequency, over a number of frequencies, a frequency range, they can give you the VSWR as being less than 1.1. That would be phenomenal over your frequency range. It could be less than 1.3 of your frequency rate, over your frequency rate. So practically, your VSWR, the closer to 1, the better off you are. Now, if somebody comes and says, my VSWR is 1.8, I will say it's not good enough. 1.8, even if it seems to be very close to 1, gives you a high reflection coefficient. So VSWR is an absolutely important number. And next time when we come together on Monday, we're going to see this on the Smith chart, and then we're going to do a matching problem. We'll start on Monday, and then we'll do all of this next week. And the week after, we're going to have reviews. Any questions? So thank you for giving me the opportunity to go through this material, because I wanted to cover the VSWR today.
I was wondering if you could explain one more time how you got rid of the cosine squared.
Oh, I have a question on that too.
Yes. Where at what point? Here. 0.436 cosine squared. I borrow.
Oh, Dr. Katehi.
Can't see your screen.
Yeah, your screen
I
is
cannot see your screen. Okay, so
Yeah.
go to your see, bumped me out. Go to your formula, and maybe that's where I had 1.33. Yeah, go to your formula, the one that I had above, and you will see. All right, so I think I made some corrections and they were correct in the first place. I will put the correct. So go to your formula. Let me just correct something and I will tell you how I got that. Okay.
Yeah, Dr. Ktai. So you had 1.33 squared minus 0.66 squared to get the original number, and that's
It's
1.33,
9
right?
o'clock.
Yes, 1.33, correct. So
But then you changed to the other number because but when I like
no,
verified
no,
myself,
correct. I made a mistake by changing it.
oh, okay. So
It
now
was
it all
correct.
makes sense. Yeah,
Yeah.
I see.
So
Thanks.
I have 0.436 in the cosine, and then I borrow a 0.436 from where it was in front of the sine, and that gives me, I will sit down and do the, before I upload it, I will check my numbers. I will put also something in between to see how I grouped my cosine with part of a sine to get the same coefficients, and then what is left over after that. All right, so let me introduce one more line in my notes to see how I grouped the two, because I skipped a line and that may create some issues.
Okay, that works.
Okay, I need to go over and check it before I upload them. And so I think the original numbers were correct, but I will check them out. All right. So, but you have a sine square with a with a number in front of it, with a constant in front of it. You have a sine square with another constant. You identify the lowest of the two constants. You take, say if it's cosine, the cosine square, you take that, and then you take a part of the sine square, which is equal. So you put the constant times sine square plus cosine square in a parenthesis, that gives you 1. And then whatever is left over for the other sine square.
Okay, I think I see what you're saying. Yeah.
So, but I will check my numbers before I upload it, and then just go through to see. I think it's very extensively written, so you should be able to identify it.
Okay, thank you so much. I appreciate that.
Sure. Any other questions?
Yeah.
Yes.
Dr. Kate.
Yes.
So we can also verify the numbers like the Vmax and Vmin with the new formula introduced,
Yes.
which is
One
the ratio.
plus, yes, 1 plus
So
magnitude of gamma L, 1 minus magnitude of gamma L.
yeah, so in this case, the max will be 1 plus the ratio the reflection coefficient, which is 1/3, so that'd be 1.33, right?
Okay, yes.
And then the
Minimum.
the min will be 1 minus 1/3.
Yeah,
That'd be
0.66
0.66.
something. Yeah, and then of course each one of them by themselves, they have also a magnitude of V naught plus. So it's the ratio, you know, exactly.
Yeah.
Yeah, okay. Yeah.
And in this case, we have V naught plus as 1 volt.
No,
right?
we don't know. No.
Oh, it's not given?
No, it's not given because I have not given you information about the input source. So, yes. So
when we were like plotting the graph, were we just assuming that it's
yes,
1?
yeah, you saw that I put a V naught plus there in the graph. You don't see it.
I drew it myself. Yeah, I see it. Yeah.
Yeah, there is a V naught plus there, magnitude, and that's there exactly.
Oh, okay.
Yeah. So you don't know exactly, you know the relative numbers, but you don't know the absolute values.
Got it. Thanks a lot.
Sure.
Professor?
Yes.
When you were solving for the current, initially you set it equal to V naught plus, well, like the V naught equation, but then you also divided by Z naught.
Yes.
And then when you went to solve for the magnitude, like you kind of excluded Z naught. Was there a reason for that?
Yes, the reason is that I forgot.
Okay.
So I'm gonna put it there. Thank you for asking me. Yeah. Any other questions? Thank you, by the way. Any other questions? Okay, so I will see you in the office hours today or on Wednesday. Well, today's Friday. Sorry. I will see you in the office hours on Sunday.
Thank you, Dr. Kasey.
Yes. Go ahead.
Oh no, I was just like, I was on my way. I was just saying thank you.
Oh, okay. I thought you had a question. All right. Thank you, Lauren.